Welcome back to the Manifest Your Wellbeing series. I'm Leandro, your Wellbeing and Nutrition Coach. This is the episode number 5 where we talk about breathing. In the Manifest Your Wellbeing series, you get information about mental attitude, nutrition, and exercise. And this is part of the Manifested Wellbeing program. This is the episode 5 of 21. And in the last video I spoke about emotions, as well as some theories related to emotion. In this video we are going to talk about breathing and respiration. We are going to cover the mechanics of breathing, as well as the effects of breathing on health and on emotion. I use breathing, meaning the movement of air in and out of the lungs, and sometimes I'm going to use respiration, the term meaning the movement of oxygen inside a cell and carbon dioxide outside the cell. Mechanics of breathing. Let's start by having a look at the structure of the respiratory system and its main components. The respiratory system can be divided in two main parts. The upper respiratory tract, which is situated outside the thorax, and the lower respiratory tract situated inside the thorax. The upper respiratory tract is composed of nasal cavity, pharynx, and larynx. Also, the mouth is an accessory part of the system. The air can be inhaled both through the nose and the mouth. The lower respiratory tract consists of trachea, alveoli tree, and lungs. When air gets into the lungs, it is distributed across its network and air exchange takes place where oxygen gets into the bloodstream and carbon dioxide is released. The lungs don't expand or contract by themselves. This movement is done primarily with the diaphragm and the thoracic cavity, with the respiratory muscles around the thorax and rib cage helping the process. The diaphragm is a sheet of muscle that is connected to the thoracic cavity at the end of the rib cage and separates the lungs and heart from the other organs. The diaphragm helps with inhalation and exhalation. When it contracts, the lungs expand, filling with air, and when it relaxes, the lungs are compressed, expelling the air inside it. The thoracic cavity also has an important role in breathing. When the chest moves, the rib cage can enlarge or contract. When the diaphragm contracts, it enlarges the volume of the thorax. The lungs, diaphragm, and thorax work in harmony, creating movement as breathing occurs. The heart is an integral part of the system, as its rates also influence the respiratory rate. Pulmonary gas exchange. The body has 3 energy systems working together to provide the energy needed for all the bodily functions, and one of them is aerobic. It needs oxygen to function and is predominantly used where there is medium to low intensity physical activity. One of the lungs' function is to take oxygen from the atmosphere to enter the circulatory system when we breathe in. The oxygen molecules are then captured by the red blood cells and transported throughout the body to be used by the cells in the aerobic energy system. When energy is created, byproducts and waste are produced. Heat is generated, water is created as byproduct, and carbon dioxide is the waste which has to be dealt with and extracted from the body. The air we breathe is composed of nitrogen, oxygen, and to a lesser extent CO2 and other gases. The more humidity in the air and the higher the altitude, the less the concentration of oxygen there is. When we breathe, the air gets into the lungs. The heart pumps blood coming from the organs, passing through the lungs and going back to the organs. The heart is heavily involved in all these processes, but today we will mainly focus on the respiratory system, and excuse me if I left out important functions performed by the cardiovascular system. It could be dealt with in another video. Just let me know in the comment section if you would like to see more about the cardiovascular system. The arterial blood travels from the lungs to the whole body. The lungs expand, bringing air in. The oxygen gets into the blood, and the arteries irrigate organs and muscle tissue with oxygen-rich blood. The venous blood that travels from the organs and muscles comes saturated with CO2, which has to be eliminated from the body. The heart pumps it towards the lungs, and then the CO2 crosses into the lungs and is breathed out. Respiration happens when gas is exchanged. It happens where O2 enters the circulatory system and CO2 leaves the system via the lungs. The oxygen available inside the lungs is absorbed, then attached to red blood cells to be transported throughout the body. The more physical activity, the more energy is created, more O2 is used and CO2 created, and lungs and heart will have to work harder to increase the pulmonary gas exchange rate. Control systems that regulate the respiratory process. There are two separate control systems regulating breathing. One is automatic and the other is voluntary. They are located in different parts of the brain. Automatic control of breathing. The automatic mechanism that controls breathing is composed by pacemaker neurons that do rhythmic electrical discharges, which induce breathing rhythms, and this mechanism is located in the medulla oblongata. The medulla is part of the brainstem. It is the posterior part of the brain and connected to the spinal cord. This is what allows us to breathe without having to make any conscious effort, something similar to the pacemaker cells located in the heart, which fire and activate the heart muscles to contract. The pacemaker neurons responsible for regulating spontaneous breathing are themselves regulated by the amount of oxygen and carbon dioxide present in the blood and its pH level. A rise of carbon dioxide or hydrogen ions, or instead a fall in oxygen on the arterial blood, increases neuron activity in the medulla, and in turn it increases the rhythm of breathing. Voluntary control of breathing. When we voluntarily control our breathing, it is done via different neural controlling mechanisms located in the motor cortex, which is responsible for voluntary muscular movement. When you decide to change your breathing patterns, the motor cortex takes over by sending the command to the respiratory motor neurons passing through the medulla and spinal cord. Even though respiration can be voluntarily controlled, the signal from the motor cortex can be overridden by automatic system, which we spoke about, and by the hypothalamus as well. Other systems affecting breathing. On the top of the automatic and voluntary control systems, breathing is also influenced by the limbic system. The limbic system is the part of the brain that includes the hypothalamus and amygdala, among other important regions, and is concerned with emotions, memory, and motivation. The limbic, automatic, and voluntary systems are connected and working together to regulate breathing, each one playing its part. The hypothalamus makes the link between mind and body. It is closely connected to the amygdala and is in charge of regulating the body's homeostasis as well as regulating emotions. It regulates emotions by being the route which emotional states can be expressed by bodily functions. The hypothalamus is also involved in the regulation of breathing. When there is high concentration of CO2 in the blood, the hypothalamus cells are activated, and by doing so, it increases respiration rate. The amygdala is a center of emotion, social, motivational, and learning processings, and plays an extensive role in regulating fear responses. Fear responses are produced by the stimulation of the hypothalamus and amygdala. The amygdala is responsible for the fight or flight responses, which can alter breathing patterns, breathing, exercise, and emotions. Now that we have a basic idea about the mechanisms responsible for breathing, it is time to have a look at its relationship to exercise and emotions. When we engage in exercise, it creates distress. The respiratory system has to deal with it, going through changes due to physiological effects of exercise. We have to make a distinction between a single bout of exercise, which we will call acute exercise, which responds in a different way compared to several bouts of exercise, or chronic exercise. The changes that the body has to go through to deal with acute exercise are called responses, and the changes it has to go through to deal with chronic exercise are adaptations. The body likes to stay in a state of homeostasis, maintain a stable internal environment where things like temperature, acidity, glucose, and oxygen levels are regulated tightly in a narrow range. When the body is under the effect of acute exercise, it initiates responses to reduce the stressfulness of it. For instance, a person jogging is contracting muscles, stressing it as they use up the oxygen. Then, the heart and breathing rate increase, delivering more oxygen to the working muscles, reducing the stress inflicted by the exercise. And under chronic exercise, the body has to develop adaptations, increasing the body's capacity to cope with the constant stress. Thinking about a person that regularly jogs, their body is forced to adapt by increasing its fitness. It does so to cope with the continuous demand by improving the body's maximum oxygen uptake, or the VO2 max. VO2 max is the pulmonary, cardiovascular, and muscular system maximal capacity to consume oxygen. It is the combination of how much oxygen can enter the lungs, how much can be absorbed by the arterial blood, how fast it can circulate throughout the body and be used by the cell. The VO2 max plays an important role in the endurance type sports and is correlated with performance in aerobic exercise. Now let's talk about limitations in performance. In sedentary individuals, sport performance is limited by muscular function. For fit individuals, it is limited by cardiovascular functions, and for well-trained individuals, it is limited by pulmonary restrictions. Regarding the respiratory limitations in very well-trained individuals, athletes, they can be divided in two categories. It can be intrathoracic and extrathoracic limitations. And these limitations, they manifest themselves in heavy intensity training. One limitation can be the onset of exercise-induced asthma. It can be also the narrowing of the glottic aperture, which is around the neck, and it can also be expiratory flow limitations, that you can breathe in, but you have problems to breathe out efficiently. The role of red blood cells in exercise. During exercise, the muscle cells have to produce more energy. The demand for oxygen increases and it puts pressures on the heart to increase the blood flow. Breathing rate and respiration increase to meet the demand. The red blood cells play an important role in transporting oxygen and carbon dioxide within and without the body. The red blood cell protein hemoglobin can carry both oxygen from the lung to where it's needed and carbon dioxide from organs and tissues to the lungs. In the lungs, the oxygen crosses into the blood and most of it attaches to hemoglobin. The cardiovascular system circulates the oxygenated blood to all parts of the body and oxygen is released from hemoglobin diffusing into the cells. The carbon dioxide produced by the cells reaches the blood and is transported to the lungs bound to hemoglobin or in the form of bicarbonate. When the CO2 saturated hemoglobin reaches the lungs, it releases the carbon dioxide to be exhaled. The bicarbonate splits into two molecules in order to leave the body. It splits into CO2 and into water vapor. Breathing and health. Breathing is an essential element of overall health, and knowing how to breathe properly can have many benefits beyond sports performance. The medical research on breathing has been focusing on improving health and finding techniques to help in the treatment of disorders such as dysfunctional breathing, hypertension, and panic attacks. I'm going to talk about two studies where breathing strategies have been used as treatments to disorders. On this study on the effects of breathing on blood pressure, the researchers found that slow breathing, which is around 6 breaths per minute, can be a helpful tool to manage hypertension. Before talking about the study, I would like to clarify some terminologies that are used throughout the paper. The autonomic nervous system is involuntary and regulates functions such as heart rate, respiration rate, blood pressure, and digestion. It has two separate and antagonist divisions. The sympathetic nervous system serves to maintain the normal functions of cells, muscles, and organs. Those that work involuntarily, such as the heart. The parasympathetic nervous division is dominant in moments of rest and repair by slowing things down, promoting digestion and eliminations. In non-stressful conditions, more impulses comes from the parasympathetic division, which is responsible to slow down our respiration rate and heartbeat. If the sympathetic division is too active and the parasympathetic not working as much, it can be a cause of essential hypertension by reducing baroreflex activity. In this case of hypertension, there is an increase of blood pressure due to restrictions to blood flow where the arteries constrict and the heart has to work harder. Essential hypertension is when the blood pressure is persistently high due to a restriction of blood flow where there is no other condition causing the high blood pressure. If hypertension is left untreated, over time it can damage arteries, brain, and heart. Baroreflex is the homeostatic mechanism that helps to maintain blood pressure stable via a negative feedback loop between blood pressure and heartbeat, by decreasing heartbeat when blood pressure increases and vice versa. In this study, 20 individuals with essential hypertension and 26 controls took part in the research. The subject did not drink, smoke, didn't have secondary hypertension, or were on blood pressure medications. Electrocardiogram, respiration, CO2, volume of air in and out of lungs, and blood pressure were measured during the study. The subjects of the study did spontaneous breathing, controlled breathing at 6 cycles per minute, and controlled breathing at 15 cycles per minute, used to mimic a normal rate. The slow breathing significantly decreased blood pressure without affecting heart rate variability. Breathing at 15 cycles per minute showed a significant decrease in systolic blood pressure only. During spontaneous breathing, baroreflex mechanism's ability to function was depressed in hypertensive subjects compared with control. However, at slow breathing, baroreflex sensibility increased in the hypertensive group. In this study, paced slow breathing at 6 cycles per minute showed a temporary reduction in both systolic and diastolic blood pressure in hypertensive patients by increasing baroreflex activity, reducing sympathetic activity, and controlling spontaneous hyperventilation, which in turn can destabilize cardiovascular and respiratory rates. Now let's have a look at the next paper, which focuses on self-regulation of breathing as a primary treatment for anxiety. In this paper, the authors hypothesized that breathing techniques may be used as a first-line supplemental treatment for stress, anxiety, and depression, as they are superior in dealing with imbalances in the homeostatic system that modulated emotions, compared to the medications that target neurotransmitters. Because drugs used to treat anxiety have adverse side effects such as dependency, addiction, relapse, and resistance. During stress and anxiety, there is an excitatory activity in the amygdala, hypothalamus, pituitary, and adrenal glands, causing the increasing of cardiorespiratory activity, blood pressure, and muscle tension. With slow breathing, the activity of amygdala can be reduced and the whole excitatory process can be inhibited. Cardiac and respiratory systems are less synchronized during stress, and there is an increase in sympathetic activity, increasing heart rate, and irregular breathing. During slow breathing in the inspiration phase, there is a decrease in sympathetic activity, positively affecting cardiorespiratory synchronization. Sympathetic activity is inversely correlated with lung volume, as the higher the lung volume during inspiration, the lower the sympathetic activity. Slow breathing causes the body to relax, the lungs and heart work in synchrony, and there is less excitability in the mechanism that controls the fight or flight response. Eastern approach to breathing. Eastern traditions have studied the mechanism of breathing for millennia, and breathing techniques are integral parts of Hinduism and Buddhism. Although these techniques are used for spiritual practice as well, they by themselves have many health benefits. To finish this episode, I'm going to mention passages about breathing on Hinduism and Buddhism and talk about a paper that focuses on their benefits. Pranayama is a discipline focused on breathing. It is part of yoga that has techniques designed to help the mind to concentrate, enabling the practitioner to pursue spiritual practice as well as to attain robust health and longevity. Mentions to the practice of pranayama can be found on the Yoga Aphorisms of Patanjali, a text about the theory and practice of yoga which can be around 2400 years old. I quote, "The breath can be stopped externally or internally, or checked in mid-motion, and regulated according to place, time, and a fixed number of moments, so that the stoppage is either longer or brief." Unquote. The Satipatthana Sutta is a Buddhist text about the practice of mindfulness, and it has a section of breathing. I quote, "Calm in the process of breathing, I shall breathe in. Thus he trains himself. Calm in the process of breathing, I shall breathe out. Thus he trains himself." Unquote. To finish this episode, I'm going to talk about a study where 60 young, healthy subjects were equally divided into two groups, pranayama and control group. The pranayama group were trained to perform Kapalabhati pranayama, starting with 1 minute of exercise and increase to 5 minutes twice or thrice per day during a period of 6 weeks. Kapalabhati Pranayama is a technique that involves a forceful exhalations and breathing at high frequency, and it's part of a system of body cleansing techniques. Peak expiratory flow was measured throughout the study. Baseline and post-test were compared. Peak expiratory flow is the maximum rate of a person's expiration. High levels of PEF are correlated with healthy lung functions. Poor lung functions predict the development of carotid atherosclerosis in elderly populations. It is the accumulation of plaque and obstruction of the arteries that bring oxygen to the head. The results showed a significant difference in peak expiratory flow among the two groups, with the test group having the highest values recorded, suggesting that this breathing technique can increase respiratory muscle strength and move air in and out of the lungs more efficiently by using the diaphragm and abdominal muscles. This is the end of the episode about breathing. In the next episode, I'll be talking about body posture, and if you like this content, please help me by subscribing, liking, sharing, and comment. It really helps me to know your feedback, to know what you think about this content, and also helps the algorithm as well on YouTube, Instagram, and other social media channels when you interact with the content you value. Thank you very much.